Hello, bacho! Welcome to this super one-shot explainer masterclass. I'm absolutely full of energy today, and we're going to crack electrochemistry so perfectly that you won't lose a single mark in your board exams. So sit up straight, get your notebooks out, and let's dive right in. ध्यान से सुनो बच्चों. Here is the exact syllabus we'll be conquering today. First, a water flow analogy. Then, galvanic versus electrolytic cells. Next, inside the salt bridge. Followed by Gibbs energy and equilibrium. Conductivity in everyday batteries, and finally, a board exam review wrap-up.
Section 1. The water flow analogy.
Okay, before we talk about electrons and chemicals, just close your eyes for a second and imagine a tall, steep hill. Spontaneous reactions are exactly like water naturally flowing down that hill. It needs absolutely no external push. It's like a self-motivated student who sits down to study without anyone nagging them. But on the flip side, we have non-spontaneous reactions. This is like trying to pump water back up the hill. It won't happen on its own, right? You need a motor. You need external energy. Just like an unmotivated student who needs a good scolding or an external push from a teacher to finally open their book.
Now let's bring this spontaneous flow to chemistry with redox. I want you to understand this with a relatable human touch. Think of zinc as the rich guy. What does a wealthy person do? They donate. Zinc is rich in electrons, so it gives them away. This act of donating electrons is what we call oxidation. On the other side, copper is the poor guy. He's very happy to accept that wealth. Copper takes the electrons, and this is called reduction. One gives, one takes. This beautiful little transaction is the absolute heart of redox.
This brilliantly illustrates the entire process. You're definitely going to see the Daniel cell in your exam paper. So I'm giving you a trick right now, and I want you to lock it into your brains. Khopadi mein bitha lo, as we say. The magical phrase is red cat and ox. Reduction always happens at the cathode, hence red cat. Oxidation always happens at the anode, anox. Memorize this and you will literally never confuse the two again.
Section 2. Galvanic versus electrolytic cells.
Let's see how this builds into the broader cell types. Notice the clear, direct contrast here. A galvanic cell is a machine that works for us. It produces electricity. It operates on a spontaneous reaction, smoothly converting chemical energy into electrical energy on its own, exactly like water flowing down that hill. But the electrolytic cell? Oh, it's stubborn. It uses electricity. It operates on a non-spontaneous reaction. We have to literally force electrical energy into it to make the chemical reaction happen, just like pumping water up the hill. Galvanic gives power, electrolytic demands power.
Section 3. Inside the salt bridge.
I know a lot of you get stuck here, so shift your focus. To understand the salt bridge, we have to look at a major problem that happens in our cells. I want to ask you this directly. Imagine your galvanic cell is working perfectly. The bulb is glowing, and suddenly, the light bulb just stops glowing. It completely dies. What just happened inside those beakers to cause this?
Pay close attention as I walk you through this. Step 1. In the anode beaker, positive zinc ions build up. In the cathode beaker, negative sulfate ions build up. This massive buildup of positive and negative charges traps the electrons. The flow simply stops. Step 2. Enter the hero, the salt bridge. This U-tube filled with potassium chloride in agar gel acts as the ultimate peacemaker. Step 3. It immediately sends negative chloride ions to the positive zinc side and positive potassium ions to the negative copper side. These ions neutralize the solutions, complete the internal circuit, and boom, the electrons are free to flow again, and the bulb lights right back up.
Section 4. Gibbs energy and equilibrium.
Okay, adjust your posture, because I'm putting on my serious university professor hat now. We're leaving the simple diagrams behind and entering the heavy thermodynamic math portion. We have an absolutely critical exam question to answer right here. How does cell potential link directly to equilibrium? How do we take the macro concept of a battery's voltage and connect it to the micro mathematical reality of chemical thermodynamics?
Let's break down this foundational formula. Standard Gibbs energy, delta G naught, equals minus N, F E naught. This equation is beautiful. It links the maximum work potential of a cell directly to its standard cell potential. So the absolutely crucial point here is that negative sign. If your cell potential E is positive, meaning the battery works, and the reaction is spontaneous, your Gibbs energy must be negative. They move in opposite directions.
And look at how perfectly these concepts connect. You already know from thermodynamics that standard Gibbs energy also equals minus RT natural log K. So, if we equate these two formulas, it means we can calculate the equilibrium constant K directly from the standard cell potential. This proves that electrochemistry is mathematically tied to the exact equilibrium concepts you've spent so much time learning. It's all one big interconnected system.
But bachon, we have to remember that real life is not lived in a textbook's standard conditions. Pressures change, concentrations change, and that is exactly why we need the Nernst equation. E equals E naught minus 0.0591 divided by N times log Q. We use this incredibly powerful formula to calculate the cell potential under real-world, non-standard conditions, adjusting for exactly how much the concentration has shifted.
Section 5. Conductivity in everyday batteries.
All right, take a deep breath. Let's bring all this heavy math back down to earth. Why should you actually care about these equations outside the exam hall? Well, before we get to the real-world applications, here is the exact textbook definition of molar conductivity that you need to write for full marks. Lambda m equals kappa multiplied by 1,000 divided by molarity. Simply put, it is the total conducting power of all the ions produced when you dissolve exactly 1 mole of an electrolyte in a solution.
And why does this specific conducting power actually matter? Think about your smartphones, your laptops, the electric cars out on the road, your little siblings' toys, your smartwatches. The conductivity and molar conductivity of the internal electrolytes dictate the efficiency of the batteries powering these exact devices. If the ions inside your phone battery don't conduct well, your phone goes completely dead right when you need it. Electrochemistry is literally powering your modern life.
Section 6. Board Exam Review Wrap-Up. All right, students, we are at the finish line. I want you to take screenshots or jot down notes right now because this is going to be a rapid-fire summary. This is the absolute core math you must know. The Nernst equation for finding potential in non-standard conditions, Gibbs energy to link that potential to thermodynamic work, and molar conductivity to measure ion power. Review these formulas until you feel completely confident seeing these numbers on your test paper.
And for the core theory, here's your final punchy summary. Always remember, red cat, anox. Reduction at the cathode, oxidation at the anode. Galvanic cells run on spontaneous reactions. Electrolytic cells require non-spontaneous forced energy. And your salt bridge is the hero that neutralizes charge buildup and completes the circuit. If this masterclass made these concepts crystal clear for you, Bach John, please hit that like button and subscribe to the channel for more board prep explainers.
Before I let you go study, I want to leave you with this final provocative thought. If we took your smartphone battery right now and applied a massive external voltage to it, a voltage far greater than its own cell potential, what exact chemical reversal would be forced to happen inside? Think about how a spontaneous galvanic process is violently pushed into becoming a non-spontaneous electrolytic one right there in your pocket. Ponder that, keep studying hard, and I will see you in the next explainer.